Okay, so welcome back to another video. So here's the Fourier series of the fractional part function. And today's video is more of a derivation of showing the left-hand side is equal to the right-hand side. And that is that we have that the Fourier series representation of the fractional part of x is equal to 1/2 subtract 1 over pi multiplied by the infinite sum of sine of 2 pi nx divided by n. So if you're not familiar with what Fourier series are, these are basically expansions of a periodic function f of x in terms of an infinite sums of cosine and sine functions. And the study and the computations of the Fourier series is actually splits into another subfield of mathematics, specifically known as harmonic analysis. It's also considered useful to, as a strategy, it's actually useful for evaluations of taking some, arbitrary periodic functions. If we actually can solve each of the terms, the coefficients of that expansion on its own individually, split that up, then plug that back in, and then you actually can get the solution of what the original problem is, or you can actually get some sort of approximation to, some accuracy. I don't want to go too much about Fourier series into detail because this is a derivation showing the left-hand side is equal to the right-hand side. So if we actually just start with what the definition of a Fourier series representation is, then it's also worth mentioning that there's also 3 different coefficients also being used to plug in, where their coefficients are in representations of terms of integrals. So if this is basically just we take things one step at a time using our the definition of Fourier series function, then also using the definition of what a fractional fractional part of a function is. Then, just plug in those pieces together as we actually just solve each of those terms one by one and plug them back in. And then we'll actually get to where we actually indeed just show that the left-hand side is equal to the right-hand side. So other than that, let's actually just jump right in. So if we start with some periodic function, f of x, so let me say periodic f of x, and it actually has this period. So in other words, it's saying that it actually repeats itself after to some interval that you're in between. Specific, we'll say that with period of 2 times L, okay, then we have this series representation written as follows for the Fourier series, I mean. So f of x is going to equal a sub 0 divided by 2, and add this with the infinite sum, n is equal 1 to infinity of a sub n, then multiplied by cosine of n times pi, or I'll put the constants first, then the variables. I wrote n times x first. So n times pi and n times x divided by L. Then we add this again, doing the same thing for the infinite sum, but now this is actually with in terms of sine. So b sub n is actually now our new coefficient as well. Then sine of n times pi times x divided by L. And it's also worth mentioning that I should also write down what these each of these coefficients are equal to: a sub 0, a sub n, and then b sub n. So a sub 0 is written as 1 divided by L. Then with our integral, and actually depending on it's your personal preference on how you want to look at this too. There's actually the integral for each Fourier coefficient. It goes from the bound from negative pi to pi, or you can do this from 0 to 2L of your period of f of x and then dx. That's for our a sub 0. A sub n is going to be the same thing, 1 over L, integral from 0 to 2L. We're looking at it like this way. And then we have f of x multiplied by cosine of n times pi times x divided by L. And then we have our coefficient b sub n. Same thing, just like this, except now it's going to be sine, because we have that association with sine over here. So 1 over L, and then 0 to 2L of f of x, then sine of n times pi times x divided by L dx. Missing that dx over here. And so from here, now we have to take a look at something specifically with our function given, which is the fractional part of x, which is the whole point of this video, that we want to show this derivation. So if we want to look at this function, the fractional part of x, so let me say that by definition it's written as it's equal to x and then subtract the floor of x. This is indeed periodic, as you'll see by this Desmos simulation over here, that it's actually periodic from between the points from 0 to 1 of that interval. And this actually, forms what this, geometrically, if we look at this at a graph, kind of like a sawtooth, wave. that the way the graph is curved, if we're looking at specific intervals, it's like if we're looking at as a linear function x, but from 0 to 1. But we're looking at this for all positive values, and it just repeats for every single integer, because that's where those discontinuities appear at for this definition of the fractional part of x. So as we say that the fractional part of x is periodic and has a periodicity of 1, then of course we can actually solve with this definition, the period 2L, and say that we could say that L is going to equal 1/2. So that's good enough to see that we can actually plug this back in. So with this transformation, it's saying that if we're looking at this from 0 to 2L, so now we have that with this, fractional part of x, we can say that our integrals for the bounds is going to strictly fall between 0 and 1, well, inclusive as well, strictly. Now that we have our bounds and then everything for L solved, and then of course the fractional part of the, the definition over here. So now we can actually plug this back into all our, terms, our Fourier coefficients. So now our new a sub 0, that's going to be 2 times the integral from 0 to 1 of, so this is actually going to be the fractional of x, and then dx. Our a sub n is going to be 2 times the integral from 0 to 1 of the fractional of x, then multiplied by cosine of 2n pi x dx, and then our b sub n is going to equal the same thing, except this is just dealing with sine. So fractional of x, and then sine of 2 pi n times x dx. So now from here, we can actually do one things at a time and then calculate each of these coefficients, and then afterwards we can actually just plug that back into our definition of the Fourier series, and then we're done. So let me actually just underline what the Fourier series representation looks like. By definition, of course, I say that I just had that written as follow. Then we can also see that if we take the floor of x, specifically we're looking at this from the interval from 0 to 1, it's actually going to equal 0. So I'll put that as right here. I'm going to put this on the side over here. So floor of x equals 0 for x is in between 0 and then 1. So 0 inclusive and 1 non-inclusive. And so from here, now we'll actually calculate things one at a time. So let's actually first start off with our a sub 0 function. So a sub 0, we said that that's going to equal, so substitute this back in. So 2 times the integral from 0 to 1 of x, subtract the floor of x, then dx. Then we said that the floor is equal to 0, so that's fine. So really we just have to, you can actually just use linearity for one and say that one of the integrals is 0. And so we have this to calculate. So this is 0 to 1 of x dx. I'll save that calculations. I'm just going to skip that. Obviously, this is very simple for anybody to solve this definite integral, that the value is going to equal 1. So let's actually, let me actually box this to say what our coefficients values is. So a sub 0 is going to equal the number 1. Okay, so now let's move on to our a sub n. Now a sub n is going to equal 2 times the integral from 0 to 1. Substitute this back in for the definition of fractional part of x, then multiply by cosine of 2 pi nx dx. Okay, and so we set that the floor of x is equal to 0, so we just really have to evaluate the integral from 0 to 2 times the integral from 0 to 1 of x times cosine of 2 pi nx dx. And I'm going to skip this calculation because all you have to really do to get the value is actually just use integration by parts. And after doing so, we plug all those values in from 0 to 1 after, taking the definite integral, doing all that integration by parts. And then also it comes down that you have to simplify things a little further, but, that's, I guess I can leave that as an exercise for you guys to, do that validation. But afterwards, after all this, you're going to get that the coefficient a sub n is going to equal to 2 pi n, then multiplied by sine of 2 pi n. Add this with cosine of 2 pi n, then subtract 1. All this being divided by 2 pi squared multiplied by n squared. Okay, so we have our a sub n coefficient. So let me actually box that in. And so now that leaves us with our b sub n coefficients. So now let's actually just plug this back in. So b sub n now, again, same thing. 2 times the integral from 0 to 1, x minus the floor of x, then multiplied by sine of 2 pi n times x dx. And then we set that the floor of x is going to equal 0. So 2 times the integral from 0 to 1 of x, then times sine of 2 pi n times x, then dx. Again, I'm going to skip that calculation and leave that as an exercise for you guys. But now you're going to get the value is going to equal sine, and then also do a little bit of simplifying as well. Sine times 2 pi n, then subtract 2 pi n multiplied by cosine of 2 pi n. All this being divided by 2 pi squared then times n squared. Okay, and just like that, we have found our values for the coefficients of a sub 0, a sub 0, b sub n, and a sub n. I got that backwards. No worries about that. Okay, so now let's actually plug this back in to our series representation. So I'm gonna erase this bottom over here because we already know like what by definition what these coefficients are supposed to represent. Make room to finish the rest of the work. But actually, before we get to plugging all these values of the coefficients back into our Fourier series, a little bit of inspection, we should see that if we're taking series, the index from n is equal 1 and into infinity, but they're integers. But also notice that for any integer n, then so I'll put this as for n is an integer. Then you're going to see that if I plug anything for n for the sine, so sine of 2 pi n, that's actually just going to equal 0. And no matter what you choose for n, it's actually, you do with this repeated periodicity, it's always going to equal 0. But also cosine of 2 pi n is just going to equal 1. And so this actually makes things a little bit easier because that way now we can actually just plug in the a sub n and b sub n using this, fact or the calculation that we actually just put in. So now this a sub n, so first a sub 0 is already fine on itself, so we don't need to worry too much about that. So a sub n is going to equal 2 pi n, then substitute the sine of 2 pi n for whatever integer that's going to equal 0 over here. Add this with that's going to be now 1, and then subtract 1 divided by 2n square, or 2 pi square n square, however you want to look at it. That's actually just going to equal 0, so that's awesome. And now our b sub n is going to equal to, now just plug this back in for everything we just did. This is going to be 0, then that's going to be 2 pi n multiplied by 1. Divide this by 2 pi square n square. And so this will actually just going to be equal -1 divided by pi times n. All right. So now with all this, let's actually plug in everything together for, our new values of these Fourier coefficients. And that basically just ends, today's video. So because as you can see, now we have that specifically f of x, which we said that that's the fractional part of x. If we plug this back in, so a sub 0, we said that that's 1, so that's going to be 1/2. Then we said that a sub n is going to equal 0. So this entire infinite sum is going to vanish. That's what makes it nice. Then just plug in a -1 over pi n back into here. And so now this is actually going to leave us and factor out the -1 over pi. Okay, and then now at our infinite sum from n is equal 1 of, so this is going to be sine of, and we said that L is 1/2 over here. So that means the 2 will be on the numerator. So 2 pi and x, and then all this divided by n. And so just like that, we actually finish verifying, with this derivation of the Fourier series representation of the fraction of x. Let me first put a check, and then let me actually just box in our, final answer that we actually did indeed complete this little simplification, that we have found that this is actually the exact transformation as follows. So yeah, that's pretty cool if you ask me.